Okay. So welcome everybody to our second week of Fair February on topics related to computation and welfare policy making. We are going to start today's session with Sanghamitra Dutta's talk. So now I introduce Sanghamitra. Sanghamitra Dutta is a PhD student, PhD candidate at Carnegie Mellon University. Her research interests revolve around machine learning, information theory, and statistics. She is currently focused on addressing the emerging reliability issues on machine learning concerning fairness and explainability. Her results on coded computing addresses long-standing problems and have received substantial attention from across communities. She is a recipient of 2020 Scilab Presidential Fellowship, 2019 KNL Gates Presidential Fellowship, 2019 Axel Berney Presidential Graduate Fellowship, and many other scientific awards. Sanghamitra received her bachelor's from Technical University of IIT Kharagpur. She has also been a research intern at IBM Research at Data Miner. We are very pleased to have her today, and she's going to tell us about her research towards a systematic understanding of exempt and non-exempt algorithmic biases. So I leave the floor to Sanghamitra.
Thank you so much for the introduction. Yeah, let me share my slides. Yeah, can you see my slides?
Yeah.
Okay.
But just before you start, Sanghamitra will take questions while she's speaking. If you want to ask, just raise your hand or just type in the chat. Please.
Yeah. So yeah, today's talk is about how do we ensure machine learning algorithms are not only fair but also lawful. So machine learning is entering into almost every aspect of our lives these days, including really high stakes applications such as hiring. Now, while these models are really great at learning all the patterns that are present in the data, but blindly learning all patterns in the data can often propagate biases with respect to gender, race, etc., leading to adverse effects on people's lives and also discrimination lawsuits. So, Amazon recently scrapped this AI recruiting tool that showed bias against women. Similarly, an AI grading algorithm ignited a controversy because of biases. So, all of this raises a very important question that bridges the fields of fairness, explainability, and law. That is, how do we identify and explain the sources of bias in machine learning models? So, to understand this problem, let's consider a scenario of hiring. We have some candidates from whom we will be collecting input features that go into a model, and the model decides whether to hire or not. And these features could be things like coding tests, aptitude tests, location, gender, etc. Now, to avoid bias with respect to gender, one may choose to not use gender. But it has been noted that even if gender is not explicitly used as an input, the model can still cause disparity and adverse effects with respect to gender, which is also called disparate impact. This happens because the other features may be correlated with gender, causing the final decision to also be correlated with gender. But sometimes there are certain features that might be so critical to an application that they may need to be given importance in the decision making, even if they have some correlation. For example, coding test score might be deemed really critical for a software engineering job. Similar exemptions also exist in anti-discrimination laws under the business necessity defense. This says that disparate impact may be exempt if it can be justified by a business necessity. For example, a coding test can be is critical to the software engineering job and may be deemed as a business necessity. But on the other hand, any disparity or bias arising from the other features is non-exempt. For example, aptitude test may not be deemed as critical for this job, as in the landmark court case of Griggs versus Duke Power. So this leads to our primary question that given a choice of critical features, like coding test score for this example, for instance, how do we know if the disparity is exempt or non-exempt? And towards answering this urgent and pressing question, our main contribution is the first systematic measure of non-exempt disparity, which is the bias that is not justified by the critical features. Now, algorithmic fairness is a very exciting field of research with several interesting works in the last few years. But this problem of feature-based explanations of disparity and integrating it with law has received very little attention. So now I'm going to, this is my outline for today's talk, and I will be spending most of my time on this problem of quantifying non-exempt disparity, and then very briefly discuss some other related problems that I'm working on. So let me start with our problem statement and approach. So let's say we have a set of features that go into this model. It produces an output y hat. Now we let Z denote the protected attribute, which could be gender, race, etc. The critical business necessity features are denoted by XC, and all of the other features which are non-critical or general are denoted by XG. Now the question is, given a choice of critical features XC, what is a good measure of non-exempt disparity, which is the bias that cannot be justified by the critical features? Now, once we are able to find such a measure or definition, the next question would be how to apply it in practice. So this technique is primarily for auditing trained models, that is to check if a model has any non-exempt disparity or not. But it could also be used during training as a regularizer if one wants to selectively reduce non-exempt disparity. But before we get there, our primary question is that first we need to answer is what is a good measure of non-exempt disparity? That is, how do we define something that we only have an intuitive idea about? So to approach this definitional problem, we adopt an axiomatic approach to arrive at this measure of non-exempt disparity. In many definitional works, a measure of fairness is often proposed based on some implicit desirable requirements. But then there arise situations where a wrong measure of bias or disparity leads to misleading conclusions. A good example is this Berkeley admission scandal, where initially people thought that there's an overall gender bias in the admissions. But then a critical examination under Simpson's paradox showed that condition on the choice of departments like medicine or engineering, there was no bias. So to arrive at a measure of non-exempt disparity, we adopt a rigorous axiomatic approach that draws inspiration from Shannon's approach to arrive at a measure of uncertainty, where he first derived a set of properties or axioms to find a measure of uncertainty that then led to his measure entropy and gave an interpretation to it.
So can I ask a question before you? Yeah. So what do you mean that in engineering and medicine there was no bias? Can you explain that a little bit more?
Oh yeah. So this is like overall, if there was a dependence with respect to gender, but once you condition on the choice of departments, that is among the students accepted in engineering or among the students accepted in engineering medicine, there was no bias. And I think I might be revisiting this issue of dependence and conditional dependence, like how dependence and conditional dependence can be different through other examples in the talk.
But the bias you define is like the people who were admitted were proportional to the people who applied, something like that.
So that's what I think. What is the right measure of bias is the question. Okay. But I think you can think of this as a motivational scenario than specifics. And But I think, yeah, the nuances of defining bias arises because sometimes dependence and conditional dependence may not be in agreement with each other. Yeah, so this is going to be our approach for this problem, that we are first going to look at a lot of canonical examples to arrive at a set of desirable properties that we want our measure to satisfy before we even propose any measure. And then these properties will lead us to candidate measures of non-exempt disparity that could then be used for possible case studies. And sometimes case studies can also inform examples and properties. Now, the significance of this axiomatic approach is that these canonical examples can often isolate these kinds of really paradoxical scenarios that could arise in the context of hiring, where a candidate definition or measure may fail to correctly quantify non-exempt disparity as we would intuitively want it to capture. For example, there could be really complex situations where correlations with gender can get cancelled with each other or even amplified in the final output because of the two features mixing. And it is not immediately obvious which feature should we hold responsible for bias in these kinds of complex scenarios that we see. So, in essence, our main contributions will be first a measure of non-exempt disparity that satisfies all of these desirable properties, which happens to be a causal measure. But then we'll also provide some non-causal or observational relaxations of this measure when the causal model is not known for these kinds of applications. And in doing so, we expose the pros and cons of several candidate measures as well. So now I'll first start with why popular definitions of statistical parity and equalized odds do not suffice for this problem of feature-based selection of biases. So statistical parity is defined as follows. If you're already working on fairness, maybe many of you will be familiar with this definition already. Reminder that Z is a protected attribute like gender, race, etc., and Y hat is the model output. So statistical parity says that the probability or fraction of acceptance for men and women should be the same. That is, the model is fair if the output Y hat is independent of Z. To quantify statistical parity, an information theoretic measure that is often used is mutual information. Now, I'll include the definition of mutual information for completeness, but the definition is not super important. All you need to take away is that mutual information is a measure of statistical dependence between gender and the output. And this goes to zero if and only if the output is entirely independent of gender. That is, this statistical parity holds. But this measure of fairness has faced several criticisms. And the major criticism is that this measure can sometimes enable overfairing. That is, it can accept candidates who may not meet the critical requirements. So to understand this, an example is, let's say Z is gender. We have coding test, which is highly correlated with gender. And there is another feature, location, which is not so correlated with gender. And the decision is based on these two features. So now here, if one tries to enforce statistical parity, that is remove all dependence with gender and the final output, what could happen is the model may significantly reduce the emphasis on coding test and begin to base its decisions on location, which is not a very critical feature for this particular application. So to avoid these kinds of overfairing scenarios, another measure that has been proposed is equalized odds. So equalized odds says that the model is fair if the output Y hat is independent of gender, but conditioned on the true labels. And this definition also becomes equivalent mathematically to equal fraction of false positives and true positives for both men and women. And this definition also includes perfect classifier. Like if we are able to have a perfect classifier where the output is always equal to the true labels, this perfect classifier also satisfies this definition of equalized odds. But then this definition has also faced a criticism. that it can enable underfaring. The previous one was overfaring, and this is underfaring. That is, it. So, because the definition uses the historic labels in the definition, it can propagate biases that are already present in the historic data. So, again, to understand this, we'll look at another example. So, Z is gender. Now, this time, let's say we have coding test score, which doesn't depend on gender, it's independent. But we have aptitude test, which is not critical and which depends on gender. Now, both these features are again taken to as inputs for decision making. Now, let us suppose that the historic labels that we have used both critical and general features for their decision making, like the past labels. Now, because the past labels used both of these features, let's say now, even if we have a perfect classifier that satisfies equalized odds, it could still cause disparate impact on women, and because of aptitude test, which is not a critical feature. So this kind of scenario could even become illegal because the bias is coming from aptitude tests, which is not a critical feature. So because of this overfaring and underfaring problems, in this work, our problem of quantifying non-exempt disparity adopts a middle ground between this overfaring and underfaring issue by using domain knowledge. So we are using domain knowledge to first arrive at the set of critical features and then selectively quantify non-exempt disparity, which is just the bias that is not justified by the critical features. So I'll now start with understanding the desirable properties and candidate measures for such a quantity called non-exempt disparity. The first candidate that we'll look at is conditional mutual information. So again, this is inspired from a subpopulation-based statistical parity, which is defined as follows. That irrespective of like the overall acceptance probability, what this says is that among the candidates with the same value of critical feature, there should be equal probability of acceptance between men and women. That is, the model is fair if the output y hat is independent of z, but conditioned on the critical feature. And the information theoretic measure for this is conditional mutual information, which is again a quantity that goes to zero if and only if this conditional independence holds. Now we are going to do some visualization on a very popular data set called the adult data set to see the differences between the measures that I just discussed. And I think this might also answer the question that Shahzad had. So first, we are going to look at histograms of overall predictions as well as histograms of predictions for the candidates who have a similar value of the critical feature. So when there is no fairness, there is dependence with gender in the overall decisions. But the conditional dependence is a bit less because the histograms are like less spaced apart as in the first case. Now, when you use something like statistical parity, what happens is the overall dependence becomes zero, but the conditional dependence is not zero. In fact, some conditional dependence might even get introduced, even though the overall dependence is zero. And when you use conditional mutual information, what could happen is that the overall dependence is like non-zero, but the conditional dependence is zero. That is, among the candidates with similar value of critical feature, the histograms are coming close to each other. So I don't know, are there any questions so far or okay, I'll move on. So this conditional mutual information, it satisfies, it resolves overfaring, underfaring to some degree, but this measure also now has some limitations. So the limitation of this measure is that this measure can sometimes falsely detect bias or spurious dependencies, even when a model is causally fair. So to understand this, we'll now look at another example. So again, let's say this coding test score is correlated with gender. The simplest mathematical representation for this feature is something like z plus u, where z is gender here and u is the latent random variable that denotes the inner ability of a candidate. So the underlying causal model could be something like this, where z is gender and u is the independent random variable, which denotes inner ability. But suppose the company is able to distill out is able to distill out this inner ability in other non-critical features like aptitude test. So suppose this is like a sample SCM, a sample causal model where one feature is Z plus U and one feature is U. But the model decides to base its decisions only on U, which is the true inner ability of a candidate. Now, this is a situation where the model is causally fair because the output doesn't vary with Z after fixing inner ability. Or in fact, what this means is that candidates with same inner ability are treated similarly and not differentiated based on gender. So if the model is causally fair, there should be no question of any exempt or non-exempt disparity. But here, surprisingly, this measure of conditional mutual information or conditional dependence is greater than 0, falsely detecting bias. To see this, notice that this is the definition of conditional independence, and this U can be written as Z plus U minus Z, where this is the part that corresponds to the critical feature Z plus U. So if the critical feature is fixed, this is the part that becomes fixed, and the remaining part shows spurious dependence on Z, even though originally Y hat doesn't have any dependence on Z. So because of this problem of false detection of bias, we enforce this desirable property that a measure of non-exempt bias should be 0 if the model is causally fair. And we'll revisit this false detection phenomenon again in experiments. But because of this problem, this leads us to examine another measure of non-exempt bias called unique information. This unique information is derived from a body of work in information theory called partial information decomposition. So before formally defining it, I'll try to explain it intuitively from Venn diagrams. So mutual information is the dependence between Z and Y hat, and this is the conditional dependence between Z and Y hat. And we have seen that both of these things could be 0 or non-zero irrespective of the other, which is why these Venn diagrams look like this. Now, unique information is this information theoretic common volume between dependence and conditional dependence that goes to 0 whenever either of them go to 0. So it represents the unique information about Z in the output Y hat that cannot be attributed to the critical feature XC. But the example that we just saw before lies somewhere here, that it lies outside this red region where conditioning introduced spurious dependencies that were not there originally in the dependence between Z and Y hat. So now for completeness, I'll also include the mathematical definition of unique information here. But again, the definition is not very important and an intuitive understanding is sufficient to follow the talk. The way I like to think about this definition is it's the conditional dependence when the marginal distribution between Z and Y hat is preserved, and also the marginal between Z and XC is preserved, but the joint distribution of the three random variables can vary to remove these kinds of spurious dependencies. And unique information satisfies this causal fairness property that we discussed in the previous slide. So, okay, now we have another measure that resolves some problems with the previous one. But then there are also issues that unique information doesn't address, which is this problem of mass disparity. So mass disparity is, I'll again give an example. So let's say equal number of men and women have inner ability 1 and 0. And let's say the ad for hiring a software engineer is shown to men with high inner ability and women with low inner ability. And it is not shown to women with high inner ability and men with low inner ability. So this is a very nuanced example where the fraction of people seeing the ads might be balanced across both genders. But if we examine carefully, this is discriminatory against women with high inner ability who do not get to see the ad. So these kinds of nuanced scenarios can be represented mathematically as the Z XOR U, where XOR is the mathematical function which denotes this kind of situations. And here, interestingly, the statistical parity or statistical disparity becomes zero. But the problem arises because the model is not causally fair. That is, there is a causal path from gender to the output. So again, this nuanced example leads us to another desirable property, that the measure should be non-zero for this example to be able to detect these kinds of mass disparities. Now, because of these kinds of hidden biases, we now have to get into causality and examine causal paths from Z to the output, and if these causal paths are passing through the critical feature. So again, these next two slides might be a bit causality heavy, but the main takeaway from these slides is that it is because of these masked biases that we need to get into causality and examine causal paths and finally come up with a causal measure. So this example, I'll go over a bit quickly, that it's again, the features are same, Z plus U and U. But what the model does is it can now cancel out U and only give Z as an output. So this is a case of bias amplification where less biased features are mixing to produce a heavily biased output Y hat. And because both of these features are responsible for this cancellation effect, this bias should also be non-exempt because both these features are responsible for this. So here again, all causal paths are passing through the critical feature, but there is a confounder U, which is causing problems in this formulation. So another desirable property is that all causal paths from gender to the output should pass through the critical feature, and also no latent variable should have such confounding effects. Now, all of these properties finally lead to one causal measure that satisfies all of these desirable properties. Again, this measure, here again, UX is the set of all latent random variables that is being partitioned into two subsets, UA and UB, which comes from this confounding aspect of the problem. So this measure, it does look very complex as it is, and also has computational challenges. But the point that I want to make is there is all value to first finding the right measure that satisfies all of the desirable properties, however hard it might be to compute. Because then it can also serve as a benchmark for other observational relaxations or candidate measures and help us understand what is it that those measures miss. And another point is that the unique information measure that I introduced, it actually satisfies all of these requirements except masked bias. And it is only to be able to capture masked bias that we need to get into this causal formulation. It's also good to notice that this unique information measure is actually lower bound to this complicated measure of ours. And this gap represents the masked bias. And this measure also has an upper bound, which comes from this confounder aspect of the problem. And this side gap represents the spurious dependencies that we do not want to capture in our measure of non-exempt disparity. So this measure essentially leads to a decomposition of total causal disparity into exempt and non-exempt components. But we're also able to separate out the statistically visible and mass disparities as well, which leads to a four-way decomposition of this total causal disparity. And this unique information, it essentially represents the statistically visible but non-exempt component of our total non-exempt bias measure. But again, this measure is complicated and it requires knowledge of the causal models. So what do we do in situations where we do not have knowledge of all of these U's or do not have knowledge of all of these causal models? So for these situations, we have to look into observational measures. But for observational measures, first we run into this impossibility result that no purely observational measure can satisfy all of the desirable properties that we arrive at in this work, or it cannot resolve all of the canonical examples that we have arrived at. So if we still want to use observational measures, we would have to use these measures acknowledging that they have some pros and cons and decide which one is most suited for our application. Like conditional mutual information is, I've already introduced these two measures, conditional mutual information and unique information, which have some pros and cons. And the third one is a more heuristic measure where you also condition on some other features based on some suspicions or partial knowledge about the causal model that can sometimes resolve some issues with these two measures. Now, I'll quickly go over some case studies with these three measures. So, this is a scenario where all four types of biases are present. And if we audit a model with no fairness regularizer, these techniques are able to capture all of these disparities, like total disparity, and also decompose it into all these components. But now, if we use some of these proposed observational regularizers for training, this is what we observe. Again, I'm not using the causal measure for training. I'm only using these observational regularizers for training. And the true causal measure is only used to see whether these measures are doing the right thing. So this is the accuracy and this is the true non-exempt bias. And this is this place where we would like to be, like high accuracy and low non-exempt bias. And as we see, these observational measures attain better trade-off than the proposed measure. Again, I think I'm running out of time, so I'll quickly go with these next two slides. So these two slides are important that here we show this case of where there is no causal bias, but there is this false detection of bias by these measures, conditional mutual information and conditional mutual information prime, while this unique information doesn't capture these biases. But again, there are situations where there's masked bias, and then in some situations of masked biases can be captured by these conditioning based measures that unique information doesn't capture. So with partial knowledge or assumption about these causal relationships, these measures may sometimes correctly quantify non-exempt bias. Like unique information is a more conservative measure. It doesn't falsely detect bias, but it can miss certain biases. And these two measures, they sometimes falsely detect biases, but also they capture some more scenarios of biases that unique information doesn't capture. So I'll skip these and I'll conclude here. Thank you so much for listening to my talk.
Thanks to you for the very interesting talk. Are there any questions? Okay, I just ask a very quick question about your experiments. Are these experiments run on like synthetic data? Like how?
Yeah, they're on synthetic data because the causal model is known. So, like to be able to have the ground truth non-exempt bias, we need the causal model.
And one other quick question. Where does like the motivation for studying these scenarios come from? Like, what is next?
I see. So yeah, I think that's a good question. I skipped this slide because of time constraints, but these are some related questions that I'm looking at. The first one is a broader generalization of this question, that instead of splitting biases into exempt and non-exempt, I want to understand the individual contributions of each features to biases. Like say, even in education, a student might want to know, did the bias come from GPA? Or did the bias come from GRE TOEFL scores? Or did the bias come from my reference letters? And based on where the bias is arising from, we might be able to do interventions as a society, like address those challenges in particular. Then other questions are like accuracy bias trade-offs and yeah, like which feature is responsible for these kinds of things. And there's also another problem that goes outside of fairness that I'm interested in, which is the problem of filter bubbles in social media. Like you get recommendations based on articles you read more. Like if someone reads New York Times, they'll get recommendations for New York Times more. If someone reads Fox News, they'll get articles from that news. So what happens is that a person gets quite confined within an echo chamber of things that you like and agree with, and you never get to hear the other side of the debate. So even these fairness tools, I think, could be useful in these kinds of situations where your recommendations are diversified by having some articles of the other political opinion, but it's not like totally fair, as in like they cannot be statistical parity or entirely balanced, because ultimately a person would want to read articles that you like. So there has to be some exemptions here, but still some kind of diversification. So I think, yeah, these are questions where I think these kinds of ideas could be applicable.
Thanks again. If there are no any other questions,
I have a question.
Yeah.
So, even when we don't consider exemption, there are arguments on both sides of whether or not fair learning should increase accuracy because we are removing sources of bias that harm accuracy, or harm accuracy because we are trying to be fair to groups potentially at a cost to overall accuracy. I'm curious, in your model, do you see it as potentially striking a balance where the effects of fair learning that would reduce overall accuracy are mitigated by allowing this exemption set, but the bias effects of traditional machine learning are also mitigated by, well, correcting for bias in your mechanism?
Yeah, I think that's a good question. And I think, yeah, like even in these kinds of trade offs that we look at, like using exemptions is helping, it's attaining a better accuracy bias trade off than, like, say, mutual information, which doesn't use exemptions. But I would say that accuracy is still not always the end goal, because accuracy is still a statistically dependent quantity. Like accuracy depends statistically on the features we are using and the internal statistical or causal relationships. But the choice of critical features goes one step beyond just accuracy. Like it's also a determination that is done with respect to, I think, social scientists or like domain experts, that which features should be critical and should not be critical, and that sometimes may not depend entirely on accuracy alone. But I think, yeah, it does attain better accuracy trade-off. But the choice of critical features is, yeah, not fully an accuracy based selection.
Thank you.
all right. Thanks again, and I guess I pass the stage to Cyrus now.
Thank you, Shahzad. Should we give it another minute or two?
Yeah, let's wait 1 or 2 minutes. We start at 12:11. No, maybe 12:12. Okay.
Oh, it's 12:10 already.
Yeah. Mm.
Well, I guess, okay, it's later than I thought. I guess I'm happy to just start now, and that way have some chance of making it through these slides before 12:40.
Give me just 1 second to come back.
Of course.
All right, so we are going to continue today's session by Cyrus talking about his work on an axiomatic theory of provably fair, welfare-centric machine learning. Cyrus is a 6-year PhD candidate at Brown University who specializes in computational statistics and statistical learning theory. His PhD dissertation under the tutelage of Eli Upfall lies primarily in showing novel techniques to bound uniform convergence rates, and generalization error in exotic settings. He has been applying these bounds to tasks of real-world interest, most notably in data science, empirical game theory, and fair machine learning. So I now give the stage to Cyrus for his talk, and if you have any questions, you can either interrupt Cyrus or type in chat, and we'll get more questions at the end of his talk.
Thank you, Shahzad. Yes, I do love interruptions, so don't be shy. And I want to thank Sanghamitra for setting up a lot of similar themes, so I'll do less work in my introduction. I first want to just talk a little bit about fair machine learning and why it matters and what the sort of problems I'm really trying to solve here are. It is now well understood that often machine learning systems are trained on one particular group, and then they're applied to society, which consists of different groups. Often that group A that we're training on is comprised primarily of the dreaded straight white male. And we find that our systems really struggle on other groups. And this makes sense because it's well known in machine learning that if we train our model on data from one distribution, we shouldn't expect its performance to generalize to other distributions. Yet this is exactly what is going on in practice, and this is causing a lot of problems. In fact, we find that if we have differential performance across different groups, differential performance of some abstract machine learning algorithm, it doesn't necessarily have anything to do with discrimination directly, but in the way that the algorithm is used, it often leads to algorithmic discrimination. The most serious example is probably facial recognition and policing, where, as we see in this lovely plot, darker skinned individuals and female individuals are generally less well recognized than their lighter skinned or male counterparts by these systems. And this leads to false arrests in some cases, or at least improper investigations based only on the highly incorrect results of machine learning systems. This also has effects in things like speech recognition, where the way you talk can seriously impact how well you're able to use a voice interface, other similar accessibility issues, and plenty more examples across the fair machine learning literature. And in this work, I'm asking the question, what actually went wrong? Is the problem that we are using a machine to do these sensitive tasks? Is it the data the machine is learning on? Or is it how the machine is learning from that data? So in this talk, I'm going to focus on this differential accuracy between groups issue. And my claim is that our current ML systems are trained on the wrong data, and this is well known, but also in the wrong way. And that is a bit of a subtler point. I'm going to say we should be optimizing our models with some method that is sensitive to the performance on protected groups. And I will be introducing what I call the malfair target for fair learning. And under this framework, I'm going to give a theoretical treatment of both the learning issues and the statistics issues that arise in fair machine learning. So in particular, I'm going to be working with overfitting and statistical estimation problems where something might look perfectly fair on the training data that you've given it, but if you only showed it 10 people from each group, how do you know that its performance on that small group will be indicative of the performance on the larger population as a whole? You really don't. This is the standard overfitting problem in machine learning. I'm also going to be talking about computational complexity issues that arise in learning. If we're trying to optimize a different target, we can't necessarily expect the same or even similar algorithms to even work to do that machine learning task. And I'm going to unify these ideas with the concept of fair pack learning, which gives a theoretical definition of fair machine learning and allows us to characterize when it is and is not possible. So the first thing I want to do is talk about welfare and sketch what we're actually going to try to be optimizing. So in welfare, to talk about welfare, we have to have a notion of utility, which is some non-negative, usually subjective measurement of a positive attribute. So this can be something like how happy an individual is, or how satisfied they are with something, or what resources they're allocated. In economics, it's often money, but you are not limited to speaking about utility as a property of the amount of income someone has or something like that. So what welfare does is it takes utility and summarizes the utility of an entire population with a single number. So everyone's utility is subjective, but welfare gives us a way of objectively measuring how well off the entire population is. The most popular definition of utility, often just called welfare, is the utilitarian welfare, which is simply the average utility across the population L. In this work, I'm covering a much more general notion of welfare, but this does make sense to think that, well, if I want to know how well off a society is, I should take the arithmetic mean. There's another popular concept called the egalitarian welfare, which rather than averaging over the population, says how well that population is, how well they're doing is going to be how well they treat their worst people, or how well off their worst people are. So in a society with high inequality, where some people are poor or homeless or suffer from various issues, and other people are very rich. According to utilitarian welfare, maybe that's okay, maybe that's a good thing. And by the egalitarian metric, we'd say, well, actually, it doesn't really matter how well off the higher up people in society are. The real problem in the society is that some people are really suffering. So if we want to improve the society, the way we need to do that is by improving things for the people who are worse off. So these are two notions of welfare, and there are many more, and we're going to explore the entire spectrum, but I want people to keep these in mind as we talk about welfare, that it is a general concept, and these are kind of two extremes of we're going to treat everyone exactly equally, and we're only going to versus we're only going to care about improving things for people who are worse off. So to illustrate this, here are three populations. In the first one, everyone is neutral. In the second one person's pretty happy, one person is sad. And in the third one person is just really not having a good day, but everyone else is pretty well off. So under utilitarianism, the first two are equal, and the third population is skewed upward. They're relatively happy because there's only one person that's unhappy. And of course, under egalitarianism, we see a different picture, where the first population is fine, everyone's equal. The second one, because some people are not so well off, it's a little bit worse, but not much worse off. And then that third one, even though on average people are doing perfectly well, the egalitarian welfare is actually very low. So the limitations of this concept of welfare that are relevant to what we're talking about is that utility inherently has to be non-negative, and it's going to cause serious problems if we try to extend to allow for negative utilities. Utility also has some sort of positive directness. When we talk about utility, it's always a good thing. We always want to maximize it. Otherwise, what kind of utility would it be if it were something you wanted to avoid? The other question with any type of welfare method is, well, I just gave you two welfare functions. Which one should I use? There's an analogy to worst case versus average case bounds in computer science. And the same question holds there. In some cases, we're interested in optimizing for one, in some case for another. And now I'm going to talk about what this whole spectrum looks like. There are more than just two possible welfare functions. So the power mean family of welfare functions is most interesting in this case called else, where I have some parameter p, and I'm going to take the average, so 1 over n times the sum of 1 through n, of this utility of person I raised to the pth power. So if p is large, in fact, as we take p to infinity, this quantity converges to the maximum. As we take p to negative infinity, it converges to the minimum. P of 0 is the geometric mean, which is an interesting case. And P of 1 is, of course, the arithmetic mean, which is utilitarian welfare. Here in this plot, we see that, let's say we have a population of 3 people with utilities 1, 2, and 3. Indeed, as we take P to infinity, it converges to 3, the maximum. P to minus infinity converges to 1, the minimum. And we kind of smoothly interpolate between them in a somewhat complicated way with this notion of power mean. So in machine learning, we care about these notions of cardinal welfare because welfare encodes this notion of societal well-being. And we, as mechanism designers, we select this a priori and we say, this is what I want. Now, the task of the machine learner would be, let's figure out how to optimize it. The social planning problem from economic philosophy describes exactly this. We want to figure out how to allocate goods or services in society to maximize the welfare. And we define welfare however we like to represent our societal ideal of what is a good society. So fair machine learning can be viewed as learning an optimal allocation from data. In other words, we're trying to learn a policy that it's analogous to a government policy on how to treat people, but in this case, it's something that a machine is doing, and the machine is making decisions that impact people. And we want that policy to maximize the welfare of the per group values of utility. The question is, Is this really that simple? Is the analogy that direct? What's actually new in this notion of fair machine learning? Well, in machine learning, we usually want to minimize a loss function. That should be easy, right? We're just flipping a sign. In supervised learning, we're trying to minimize our loss function over a hypothesis class. But we need to define a utility function and then optimize the maximum welfare in terms of that utility. So the obvious thing to do would be, well, if utility is good and loss is bad, why don't I say utility is negative loss? That causes no problem with the notion of egalitarian welfare or utilitarian welfare. But all the other power means are now taking fractional powers of negative numbers. Complex numbers don't save us because this is not something we can optimize if it's not real valued. So this doesn't seem to work. We can't just say utility is negative loss and then optimize welfare directly. Now, what if we did something different? If our loss function is between 0 and 1, I could say, well, why don't I take utility to be 1 minus the loss? Well, that seems to work. That fixes our issues before. We do get an answer. It is defined. But the number 1 was a little bit arbitrary. We could have just as well taken 2 minus the loss to be our utility function and optimized that. Now, if the loss function is unbounded, this does not work at all. And if we could take any constant and say, we're going to define utility as some constant c minus the loss, and it turns out as we take that constant c to infinity, we always just recover the utilitarian welfare. So there's a very there's no real justification for why we pick one constant or another, and changing that constant changes our notion of welfare. And if we said we're going to encode our societal notion of what it is to be a good society in a welfare function, then the fact that the way we define our utility function is arbitrary and can change the way that works means maybe this isn't such a principled way of approaching this problem. To fix this, I introduced the idea of malfare. In the standard setting, we want to maximize a measure of societal well-being. And if we just look at things pessimistically, I say, instead, I'm going to minimize a measure of societal suffering. So of course, the fact that maximization and minimization can be related for linear functions is just obvious. Well, at least in machine learning, that happens all the time. Minimizing loss is equivalent to maximizing negative loss. But for these welfare functions, we can't just commute a negative sign through a welfare function. It doesn't end up being the same thing for any value of p other than 1 and the plus minus infinity. So welfare is a complicated multivariate optimality concept, and our intuition from univariate optimization does not really work here. But it turns out we don't need welfare because we can just go back to why we picked welfare to be what it is and derive malfare in exactly the same way. Essentially, malfare takes the concept of welfare and considering positive utilities and flips it around and says, we're going to consider negatively connoted losses, which are still positive numbers, and try to minimize a function of those. In the interest of time, I don't want to spend too much time on the axioms of cardinal welfare, but let's just say I'm going to flash them on the screen, and anyone who's interested in classical economics might look at them and say, oh, I remember that stuff. And it turns out all of these standard axioms, which are just simple things that are very, it would be very hard to argue that you don't want them in a measurement of overall well-being. The first 5 or so, or 7, apply equally well to welfare and malfare. And there's a notion of the Pijou-Dalton principle, which says that if the average utility in 2 populations is the same, and one of them is more equal than the other, then we should prefer the population that has more equality. And if we take that principle, we constrain ourselves to welfare functions that are fair in this sense, which ends up being P needs to be less than or equal to 1. So utilitarian welfare, P equals 1, that's fine. Egalitarian welfare, P equals negative infinity, that's also fine. Everything in between is fine. But if we go in the other direction, it's not fine anymore. And that makes sense because as we take P to infinity, we recover the maximum. And if we measure the overall well-being of society as how well off its best off person was, well, we can't just look at Jeff Bezos, or I guess Elon Musk now, and say, oh, everyone in America has billions of dollars, they're rich, everything's fine, we don't need to worry about it. So this is a very good axiom for characterizing what we mean by fairness. It doesn't really work for malfair because we actually want the opposite. Because malfair is bad. So it's measuring a bad thing. So a society that's more unequal should be more bad. So we just flip the direction of the requirement of the inequality, and the inverse of the original Piaget-Dalton principle. When we're talking about measuring something bad, that's what we want. And it ends up being that we need to now take P greater than or equal to 1. So utilitarian malfair is fine. As we take P equals into infinity, it becomes, I want to minimize the person who is suffering the most, minimize the maximum suffering. Whereas in welfare, it was maximize the minimum utility. So other than that, there's no changes. The same axioms all apply, and we get that if you believe that welfare makes sense as a way of measuring how good a society is and is something you should want to optimize, you should also believe that malfair now is something that you would want to minimize. And if you can give me some notion of loss and you tell me this is a bad thing, then when I want to do a fair version of loss minimization, I can say, well, I will take a malfair function of the loss. So what are the limitations of these concepts? Well, you can think of them all as essentially mean-like functions. And as I take P to extreme values, they become more like maxima or minima. But it's a very specific class of functions defined by those axioms. And things that you might think seem innocuous actually end up violating them and thus being not well suited to being used as welfare functions. So for instance, convex combination. You might think if I have two welfare functions, I could average them and get a new welfare function. It turns out that is not correct. Constant offset, similar story. If you take a welfare function, if you just say, what if I pretended everyone had $1 more and define that as a welfare function? That ends up violating some other axioms. So that's not a good welfare function either. And in fact, we get that assuming the first four axioms, the only possible welfare functions are functions that are monotonic in a generalized mean, meaning you apply some function, you apply some monotonic transform to the average of f of x for f being some function. To relate back to power means there, f would be the pth power. Now, if I add some more axioms independent of common scale, it's not just any generalized mean, it now has to be a power mean, but it's some monotonic function of a power mean. If I add the unit scale and linearity axioms, linearity being just that changing the units won't matter. So if I convert my dollars to euros, it shouldn't change the relative welfare of societies after just making a currency change. Now, the only possibility is the power mean. So if we are interested in welfare functions and malfare functions, we should only be thinking about the power mean because that's actually the only way to satisfy all of these axioms. The Piaget-Dalton principle, of course, then says we only need to be considering P less than or equal to 1 because that's representing fairness in the sense that we want more equality. And the anti-Piaget-Dalton says, well, if we're talking about malfare, same idea, just flip the sign and we get P is greater than or equal to 1. So now we've got this notion of malfare, but in machine learning, we're trying to learn something from a finite sample of some sample of size m. And we're going to make our estimate be the empirical mean of the loss over the samples we have from a particular group. By the law of large numbers, empirical means, well, they're usually pretty well behaved. We get that the limit of our empirical mean will converge to the true mean. Therefore, as you give me more and more data, my empirical estimate of the malfare using those empirical mean losses will converge to the true estimate. So that's fine for asymptotically making this argument, but for a finite sample, we actually don't have that the expected empirical mean is equal to, empirical malfare is equal to the malfare. In the statistical parlance, this is saying that the empirical malfare is a biased estimate of the malfare. Now, to put this in perhaps more familiar terms, we know that empirical variance, or we can get an unbiased estimate of the empirical variance very easily, but the empirical standard deviation is generally a biased estimate, and we have to know a lot about our random variables in order to get an unbiased estimate. And this is kind of a similar situation because we had some square roots or pth roots or messy functions inside of these expectations. And now all I'm telling you is that because the function is kind of messy, we can't necessarily get an unbiased estimate with a finite sample. Fortunately, if we get away from the asymptotic framework and say, well, I want to know how well can I do with a finite sample? The answer is, well, I can do pretty well. The gap between the true malfare and the empirical malfare will, with high probability, be no greater than the range of my loss function times this quantity, which goes to 0 as my sample size increases at a 1 over square root of m rate. And this is just using the classic Hoeffding inequality. So it's not necessarily a very strong bound, but it does at least tell us that we do have some hope to estimate these quantities as long as our loss function is bounded of range R. Now, we can improve this a lot by looking at a variance sensitive bound. And this one, I'm basing this on Bennett's inequality, which asymptotically will give us something as good as applying the central limit theorem and basically pretending our random variables are Gaussian. And our main dependence is going to now be on the square root of the largest variance. So that's the largest standard deviation of the loss among any of our groups. So if one group has very high variance of their loss, it's going to be hard to estimate that group's loss. And because it's hard to estimate their loss, it is also hard to estimate the malfare, as that is a function of the loss. So variance here is the kind of the bottleneck that tells us how much data do I need to be able to estimate the malfare from a finite sample. Now we can go a lot further than Bennett's inequality. I'd love to go more into this, but in the interest of time, I'll just say, if we have many functions and we're trying to learn the best one, we can't just use some IID bound like Bennett's inequality or this Bennett-based bound. We instead need a way of bounding the amount that we will overfit by considering multiple hypotheses or the multiple comparisons problem. The Rademacher average is a way of doing that. And it's well understood in statistical learning theory that for many function families we'd be interested in, such as linear regression family under boundedness, finite dimensional linear classifiers, Rademacher averages and all these tail-bound terms are going to be theta of root something small over m. So again, we get the rate of convergence depends on 1 over the square root of the sample size. So if you want a better estimate of the malfare, you just need to get more samples, and this tells you exactly how many. So in classical statistical learning theory, let's again look at this notion of a hypothesis class and say this is going to be linear classifiers. We're going to build a function family called HD, which is going to be linear classifiers in the d-dimensional reals. And we're going to say, given any x, we're going to take some weights vector and the dot product with x. And if it's positive, it's class 1. If it's negative, it's class -1. And you can learn any weights vector you want. Now what we're going to do in classical machine learning is usually to optimize the risk, which will be the expectation over a sample drawn from our distribution of labeled points of the loss function applied to the true label and the predicted label. So the 0, 1 loss is going to be 1 if the true and predicted label disagree, and 0 if they agree. So optimizing the risk is just optimizing the 0, 1 loss. Of course, we don't actually know our distribution because we only have a sample. So we can't actually optimize the risk. Instead, we have to try and figure out a way to approximately optimize the risk and guarantee that with high probability, we did almost as well as if we had optimized the risk. So So the questions here are, can this class be efficiently learned? And what actually do we mean by that? Pack learning is the classical answer to those questions. In pack learning, we're going to suppose we have some hypothesis class, such as this linear family, and some loss functions, such as the 0, 1 loss. And we're going to say this hypothesis class is pack learnable if there exists some algorithm such that for any possible distribution over our labeled pit points, for any failure probability delta, so we're going to want a high probability bound, and that probability that things go wrong is going to be delta. And for any additive error guarantee epsilon, A will be able to identify a hypothesis in the class such that with high probability, the risk is going to be, the true risk of the function I identify, the function I learned based only on the data, will be no more than the true risk of the optimal function over the entire hypothesis class, which I have no way of knowing, plus epsilon, where epsilon was the user provided parameter. Now, how much data do I have to look at in order to answer this question? Well, that's going to depend on what is epsilon? So how strong of a guarantee, how strong of an additive guarantee do I want? What is delta? So what's my chance that my randomized algorithm could have gone wrong over this process? And what is D, which is usually going to be something like the dimension of the linear classifier. It depends on how you define your hypothesis class. So this is a classical concept. It has nothing to do with fair learning, but it does tell us what we mean by being able to statistically efficiently learn something, and how we want to be optimizing risk, and how we could expect to get a guarantee on the risk over a distribution without actually looking at that distribution. Now, we may also say we care about computational efficiency. There may exist an algorithm, but if it takes unbounded runtime, you won't actually be able to run it. And if you can't actually run the algorithm, philosophically, is that any better than not having an algorithm at all? There's an argument in either way. But because people do care about this, we've said there's a notion called efficient pack learnable, which will require all of this, and also that the time required for this algorithm to select this h hat function must be polynomial in all of these same parameters. So in my work, I've said, let's take this notion of pack learning and put the word fair in front of it and define what we want that to mean and see if that class is also interesting. So again, I'm going to suppose some hypothesis class and a loss function. Those really look the same. And now I'm going to say it's fair pack learnable if there's some more stuff in the for all. I don't just have one distribution now. I have a distribution for each of my protected groups. And each protected group has points and labels associated with them. The failure probability and additive error epsilon, those are the same as before. Now, I'm also going to say for all fair malfair functions, that's going to be power means with p greater than or equal to 1. I need the algorithm to be able to identify a hypothesis where I tell it all of this stuff, and it picks a hypothesis requiring sample complexity that, again, is finite. Now it can also depend on the number of groups we're dealing with, such that with high probability, the hypothesis I've learned obeys that its true malfair is less than or equal to the true malfair of the optimal function plus epsilon. So it should look very similar. All I have done is said, when I only have a single class, I only need to look at risk or expected loss. Now I have multiple classes, so I need to consider the risk of every group. Sorry, now I have multiple groups, and I only need to consider the risk of every group. And then I wrap that inside of a malfair function, and I say, I want to learn something that is approximately, or epsilon, malfair optimal with high probability. So does this capture a valuable or generic notion of fair learning? I'm arguing that from the axiomatic justification of malfair and the social planning problem, yes, this is a reasonable way to interpret what we mean by saying, I want to do machine learning except consider fairness across multiple groups. Now, a bigger question is, do such algorithms exist? Is it ever even going to be possible? There were a bunch of for alls here. It might be very difficult to actually make an algorithm that would work for any possible fair malfair function. And third, well, this is very derivative of the pack learning framework. So is there a connection between them? I would hope so. In fact, I find that yes, of course, the answer to all these questions is yes. Otherwise, I probably would not ask them on the slide because that would just look silly. So first, let's talk about realizable learning. In this case, we're going to assume that there is a perfect function in our hypothesis class that gets everything right for all groups. This is an easy case of learning because all we need to do is worry about overfitting, in that if I only look at one or two samples and a function gets them right, it doesn't mean it will get every possible sample from the distribution right. So we need at least some large number of samples. And then given these samples, can we find these optimal functions that are always right? And will they generalize to more samples? In general, we're not going to assume that there exists a perfect function. But when we just talk about the realizable case, everything is easy, because if we have an algorithm for realizable pack learning, we can essentially use it for fair realizable pack learning by showing it samples from all of our groups.
Sorry to interrupt, but you have only 1 more minute, Cyrus.
Thank you, Shahzad. So, given this notion, we can say that fair pack learning and pack learning end up having a bunch of reductions between each other. And if you can do fair pack learning, you can always do pack learning. The converse is sometimes true. In particular, if we have a no free lunch assumption, meaning that essentially statistical or uniform convergence, meaning every function every loss function in the family, its expected value converges to its empirical value, then all of these concepts are equivalent. And if you can pack learn, you can fair pack learn, and vice versa. Same concept. So there's actually not much interest in theoretically distinguishing them. The last thing I want to say is we didn't talk about efficiency yet. The story changes when we introduce efficiency, and essentially, to my knowledge, it is not the case that if you can efficiently or in polynomial time pack learning, you can also fair pack learn it. Although most of the conditions under which pack learning are possible also imply that fair pack learning is possible. I think I will close the talk there and open the floor to questions.
Thank you. Are there any questions for Cyrus? So I have a question. So when you were talking about the speech recognition application, I actually thought of an example that I am dealing with it every day today, or every other day actually. So if you look at the transcripts that, for example, you see on Zoom, like for somebody for whom English is not the native language, you will see that the speech recognition is able to understand some words that I pronounce, and some words are like really far off. Now, I sometimes think this is good if it is not fair against me, because I realize that, you know, the students who I'm talking to may not understand my pronunciation on that word. So I guess if machine learning, like, it's also the issue that Sanghamitra talked about, that we don't want things to be like overly fair. Like if machine learning understands my accent better than my students, maybe that's not what I want. So I guess the way it gets related to the topic you discussed is that maybe we don't want to maximize or minimize malware among all the groups. Maybe we want to have like a weighted thing that, you know, maybe you don't want the machine learner, the like algorithm, to be able to understand my accent better than the population does. Something along those lines. Yeah, that's all I want to say.
So I think that's an interesting point. And I see the perspective. Your goal there is to be understood by your students, who are going to be around half native speakers from America. So maybe your accent might confuse them, although I find it very easy to understand. But is there something inherently worse about your accent than, for instance, in Eastern Seaboard accent? If you were British, for instance, you could easily make the case that perhaps the way you speak is actually much better than the way I speak, and it's the way the English language is supposed to sound. And that's an opinion, but you know, you can't necessarily say one accent is objectively better than another, and declaring that by fiat, which is implicitly what we do when we create a speech recognition system that works better on one group than another, does bring with it the bias of their creators and what they think is a better accent. So maybe there is some value in some cases of having a recognition system that works better for one group than another, but that also brings the bias of the creators of the system rather than trying to serve the people who want to use it.
Yeah, I understand your point. Like, I mean, I guess it's a very philosophical question, but I guess what I mean to say is that perhaps we want to have a model whose functionality is consistent with the actual population. Like, it's not only that I care about, I mean, it's not only because my class is white males that it's not about gender anymore. White people or Native Americans who I care about. Like, if you make a film that like a not native speaker is speaking in it, maybe a lot of people who have, I don't know, who are watching it internationally would not understand that accent either. You know what I mean? Like, for example, I don't understand that. I usually understand the accents of like Iranians and native speakers better than, for example, some other countries. You know what I mean? So it's kind of like, I think the bias should be consistent of, it's not always bad to have some bias because that's what actually comes from the real population.
That is an interesting point. And I think that's one of the things we can do by tuning the welfare function.
Yeah, I think like if you have some, like if you find a, like, if you find a linear combination of them rather than like minimizing overall subgroups, maybe that would be another interesting thing to consider.
So I think that if we consider the utilitarian welfare, but we weight by the size of each population, that would potentially address the situation you've described pretty well.
Yeah, or maybe I would say take the minimum over the average of 3 groups. So you will have something in between this. You know what I mean? I have to end this discussion now because we are out of time, but I would like to thank again Sanghamitra and Cyrus for their very interesting talks today. And I would like to encourage the audience to continue this discussion at 2 today. So thank you all, and let's thank our speakers again.